Hello Internet, my name is Quinn and this is Blondihacks. I've got some projects coming up where I'm going to need to round the ends and corners of a lot of small parts. So I thought it'd be worthwhile to build a fixture for this that'll take care of it for now and forever. So let's go. This is the design I have in mind. It's a Morse Taper 2 shank that goes in the center of my rotary table, and then it has a series of these insert fixturing pins that go in the top of it there. Most of the time when you're rounding an end of a part or a corner, there's going to be a center hole that marks the center of the radius that you're trying to round. So these pins have a hole in the center, and then the center of the mandrel is threaded and can be used as one of the fixturing points for the piece, making for very fast, easy setup. The other secret sauce on these pins is that they all have a shoulder that's larger than the registration radius and elevates the part above the table the same thickness as my parallels to give clearance for the cutter. Then I just make a series of these pins for different sized center holes. For the really small sizes that are too small for the bolt, there's just a pin and it relies on external fixturing, as you'll see here later. Here's my target for this fixture. It's my 6-inch Vertex rotary table, hashtag not sponsored, and it conveniently has a Morse Taper 2 in the center of it, which is going to be the basis for my fixture. I want to start by making keys for it. You can see that the factory has included key slots here with threaded holes, and those are so that you can make keys that fit your T-slots on your milling machine and very quickly set the table up every time and not have to dial anything in. Now I have this scrap of steel here that's slightly bigger than the keys, so I'm going to try to use it. Now this scrap is just barely big enough for this, but I'll squeeze these keys out of it, as you'll see here. So I'm going to start by milling this flat step off the top of it here. I've got my copper wire in there to keep the movable jaw from influencing the position of the part there, since this block is of unknown squareness. And then I put that side I just machined up against the fixed jaw and machine the side 90 degrees to that. Then the 90-degree corner I just made goes down and back in the vise as reference for the remaining two sides. This is all just standard squaring up material method here. And then I've machined it down to what I think is the perfect dimension for a very close slip fit in that slot there. And that looks like that's going to work. There shouldn't be any wiggle in that, or else of course it's not going to be an accurate reference key for the table. The table might end up in a slightly different place every time if the keys can move. To figure out how big to make the T-slot side of it, I found a stack of gauge blocks that's just the right fit for my T-slots here. I'm looking for a fit that is very, very close to where I can slide it in, but it's not going to wiggle once it's in there. So I've got to get that just right as well. Centering up on the block there, and I proceed to cut the sides here down to the dimension that I measured with those gauge blocks. You can see there's some old machining marks there and a hole in the middle of this chunk and, various other features that I don't want, but I'm doing my best to kind of work around everything here to squeeze these keys out of this piece of scrap so that I can use it up. Once I've got that dimension just right, then I can go ahead and flip it over and machine the key down to final thickness. The thickness is important here because the wide part can't stick down below the bottom of the rotary table, or of course the table won't sit flat. So that looks really good. I've got a very close fit, and the shoulder is below the bottom of the rotary table. Now I can cut this block into two so that I end up with two keys. You can see that I've machined part of that hole away that was in there. A little bit of it is going to remain. I've got just enough material to where I can squeeze these two keys out of here if I kind of work around the features that are there. And none of this is going to matter because these keys are going to get bolted to the bottom of this table permanently and you'll never see them. So a few little nooks and crannies like that won't hurt anything. And I do like being able to use up every last scrap of material. Then I just need clearance holes for the bolts that go into the table. I'm center drilling and clearance drilling these holes through, and I've got an end stop set up there so I can just swap out the other part and not have to remeasure anything since these two keys are the same. Now I also need to countersink these, so I've got this bolt-on wobbly looking countersink thing. It's actually designed for woodworking, but in a pinch it does work in steel, and it has the right angle on it for the countersink bolts that I'm using for this. I just trial and error my way down on the depth there until the bolt head sits flush, or mostly flush. These don't actually have to be flush because the bolt head sits down in the open part of the T-slot anyway, so it's not going to interfere with anything. There isn't quite enough meat here to get those completely flush without cutting into the sides there, so I stopped there. And then I'll do some deburring on the table itself. You know, these import tools, one of the areas they cut corners on is deburring things, so there's always little snaggle tooths on all the cuts and threads and things. I'll do a little test fit here and see if those keys seat in there nice, and they sure do. Those are looking very good indeed. Moment of truth. Let's see if the table will sit down on the two keys using the middle T slot there. And it's very, very close. You got to get the alignment just right, which is what I want. It should be tricky to get it aligned, or it probably isn't accurate enough. And that is perfect. It sits down on there, but it won't move. And I think that's going to be really repeatable. Very happy with that. All right, on to the next part of this fixture now. The basis of it will be a Morse taper pin that goes in the center of the rotary table and has a series of little fixturing elements that I can attach to it. So to make that Morse taper, I've got another piece of scrap here in the lathe, and I'll face the end off of that, as is tradition. Then I punch a number 2 center in the end of that, and you might think that is for tail support, and well, it is, but I'm also going to flip it around and then face and center punch the other side of this, because we're going to be turning this between centers. Why am I turning something between centers? It doesn't need to be that accurate. Simple, we're going to be offset tailstock turning this, so that has to be done between centers because you can't hold things crooked in a chuck, at least not intentionally. So I've got it between centers there, and I start by turning this down to the OD of the large end of my taper. So this is a Morse taper 2, so I need a 700 thou OD at the big end. You can get that data from Machinery's Handbook. Now I can set up 2 indicators, a long travel one on the carriage and a regular one on the cross slide, and I can use those 2 indicators to set the offset of my tailstock for the taper turning. I'm adjusting the tailstock until I see 50 thou of travel on the cross slide indicator for 2 inches of carriage travel, and that gives us 50 thou per inch of diameter change, which is a Morse taper 2. If you want more details on this whole process, go check out my video on turning tapers that I did recently. I covered a few different ways to do this other than the offset tailstock method, but I chose this method here because it's most accurate, especially on a hobby lathe, and it's one of the few ways to get really long, gradual tapers like Morse tapers on small machine tools. So I just keep doing passes until the small end is roughly the size that the Morse taper spec says it should be. That measurement can be fairly approximate because the diameter of the small end just sets the final lateral position of this arbor in the center of the rotary table, and that's going to be pretty flexible, as you'll see here in a moment, because I'm going to be adjusting wherever this happens to land. And I also hit it with some emery there just to improve the finish, because the better the finish is on a Morse taper, the better it will hold. And if you want to be really sure, you can put some Prussian blue on your shiny new taper here and do a test fit on the mating taper or some other taper that you want to use as a comparison. In this case, I'm using my tailstock because it's as good a Morse taper 2 socket as I have anywhere in my shop, so it'll be good enough for this test. And then you can check where the blue has rubbed off on the other surface, or if you can't see in there, then you can see where it's gotten thin on the part that you created. And if that fit isn't satisfactory, you can fine tune it from here with more emery and then blue it up and check it again. But I'm happy with that. So now to set the depth of this taper, as I said, it's going to land in some arbitrary place. So I'm going to roughly mark the top surface of the rotary table there. And then I'm going to rough cut it a little bit proud of that line here on the bandsaw. The key to this fixture is that the end of this Morse taper has to be perfectly flush with the top surface of the rotary table. So here's how I'm going to do that. I seat the bandsaw cut piece in there, and the part that sticks up is used to dial it in on the center of the spindle there with the coaxial indicator. If you haven't seen one of these before, the motion of the needle is indicating run out for you, so you just adjust the hand wheels until that needle stops moving. These things are an interactive and fun way to achieve concentricity on the milling machine. But now how do I machine that flush with the top of the table without cutting into the table? Here's how I'm going to do it. So I've got a feeler gauge there, and I'm finding a spot 10 thou above the top surface of the table on the end mill there. And then I zero the quill DRO on that spot, so I know that minus 10 is the top surface of my table. Then I just go ahead and mill down this shaft here to 0, so I'm now 10 thou above the top surface of my table. And then I just need to bring that shaft down another 10 thou without touching the table. How do I do that? Well, end mills come in two basic types. The normal kind on the left there, see there's a hole in the center of it there, and the center cutting type shown on the right. Two of the flutes meet in the center there. The latter can be plunged straight down into material. You can also, of course, do this with two flute end mills, but a 4-flute is what I happen to have here for this. So what this allows me to do is plunge straight down into the middle, that remaining 10 thou that I need, and then I can move the cutter right up to the edge of my mandrel without touching the table, and then just rotate the table. I'm effectively doing a spiral cut here, and I'm just moving the table laterally a little bit at a time until I confirm that the edge of that cutter has removed all of the material without touching the table. There's a little bit of a chamfer on that center bore there of the table, which gives me some wiggle room on that. And then if I've done my job right, I should be able to set a parallel on there, and it shouldn't rock in the middle, and there shouldn't be any daylight underneath the parallel over the mandrel there. And that looks really good. So I think we're as close to perfectly flush with the top of that table as I can get it. The next step is easy. The fixture needs a threaded hole all the way down the center of it, or most of the way down. And this is for a bolt that clamps the piece to the center of the fixture here. Most of the time there's going to be a hole in the part that we're rounding, so might as well use that hole as one of the fixture points. Next I need to make the counter bore here for the center where the fixturing pins go. And I'm going down with a smaller than final size 2-flute end mill here because the correct size end mill that I have for this counter bore is not the center cutting type as I showed earlier. Note that end mills don't actually make a flat bottomed hole because they have clearance angles on the flutes on the underside. So I will end up with a little bit of a peak here, but that's okay. I'm going to be compensating for this later. If that mattered, you'd want to use a boring bar for this. So I'm clearing out the center of the material with the 2-flute center cutting end mill, and then I can finish it out to final diameter with the regular non-center cutting end mill. This end mill will leave the perfect ID that I want for the fixturing pins that fit into this center here. Now doing this with an end mill does mean the hole is going to be a little oversized. You'd want to use a reamer or a boring bar if the dimension had to be perfect, but I can turn the pins to suit. I'll get that nice and clean now and measure the final depth that I landed at. I mean, I had a depth in mind, and I used the quill DRO to hopefully hit it, but I need to know exactly what I did land on so I can make the pins to suit. It doesn't actually matter what this depth is, as long as I know what it is. But, well, yeah, I got within a couple tenths of what I was aiming for, so happy with that. Now I can go back in and thread that hole. I actually only drilled the tapping drill size earlier, and so I'll come back in and thread that all the way down. And a little deburring and a little cleaning, and this part of the fixture is done. That was the trickiest part. The rest is pretty straightforward. I just need to make a series of like little cartridges of a sort that go into that counter bore to suit the various hole sizes and corner rounding setups that I want to use. So I've got a scrap of aluminum here that I'm going to use to make these pins with, and I'll face that off as is tradition after having to fix my center height on the tool. And then I'll turn this down. So I'm making the first of several of these pins. The first one is going to be kind of an experiment. I mean, I'm going to try to make it right the first time, but I'm also going to be using it to establish some of the final dimensions for all these pins. So I'm making the one with the simplest geometry first, just to make sure I know what I'm doing. So after turning the OD to the same as my counter bore in the mandrel there, then I set the tool on the end of the part, and then I'm using an indicator on the carriage to get a very precise shoulder depth here. This shoulder depth has to be just right. You'll see why here in a moment. Now I can knock those sharp corners off, and I'm going to center drill and clearance drill this for the center bolt. Once again, on all the larger size pins, there's room for a bolt to pass through the center and act as one of the fixturing points, so this just needs to be a basic clearance hole for the size of thread that I put in the center mandrel there. Now I'm carefully finding the edge of the part with my scale, and I'm going to part it off to length, but I'm going to leave it, 20 thou long, and then I'll face it down to final length, because once again, the length of this pin overall is very critical. And Yahtzee. So it's been left long right now, and I'll seat it down in the mandrel there, and I'm going to measure how high that shoulder is off the surface of the table. And that mandrel is also a little loose in there. I'm not very happy with that, but we'll deal with that later. So I measure the height of the shoulder, which I'm deducing from the overall height here, because the shoulder height needs to be exactly 125 thou above the surface of the table, because that's the thickness of my parallels that are going to be used for packing the other end of the fixture. So stay tuned to see how this all works. So I got it flipped around here now, so I can face it down to the exact length. And here's a trick that I think I learned from Prezzo, Mark Presling. I'll link to his channel below because it's awesome. You use the end of your Jacob's chuck and you just loosen the jaws slightly and press it up against there, and that squares the part up in the 3-jaw chuck. And this is good to within about 1 thou here, as you can see on the indicator. And then if you need it more square than that to the jaws, then you can tap it in from here. But this is good enough for our purposes. And then once again, using the indicator on the carriage to measure the exact amount to face off so that I hopefully end up with the exact right length here. I'm doing all of this by measuring right from the fixture on the first part, because that way I don't have to rely on getting all of my, cuts perfectly the right depth and everything on the mandrel. And from now on, I have these measurements for all the rest of these pins. I know how long to make the base, and I know how tall to make the shoulder and so on, so that everything lands in the correct place. So final check here. I'm using a 125 gauge block there, which is the same thickness that I want for the packing material, to make sure that that's at the same height there. If those are perfectly at the same height, you can actually tell with your fingernail, just running your finger over that, you can tell if you can feel an edge there on the gauge block or on the shoulder, they're not at the same height. And you can also tell just by using some magnification and just looking. If you can see the edge, then they're not at the same height. Now, actually, this is a little bit too tall, so I mismeasured a little bit. So I went ahead and made the second of these 2 fixturing pins, and I tweaked all of my dimensions ever so slightly using everything I learned on the first one. And I may keep that first one, I may not, we'll see. So here's the second size of hole. Take 2. Here's the second size of hole. Let's see how that goes in there now. And diameter-wise, that is a much better fit. No wiggle there, and it just slides in really nicely. That's really the fit I was looking for. Now check the shoulder depth here, once again, using the measurements I learned on the first one, and that's really good. I mean, it's, 6/10 over, but that's good enough for this fixture. Do the gauge block check once more, and yeah, I really can't feel an edge there at all, so I think we nailed it. And that one came out so nice fit-wise and dimension-wise that I went ahead and made the first one again because it was annoying me that it was not as good as the second one. I made the rest of the pins that way, and now let's do a little test here. So I put a hole in the center of this bar, and now let's round the end of it. So I use the smallest of the pins in the set as a tool to center the spindle on the rotary table. So I move the table around until that slides right in there perfectly. That's an easy way to get the table centered up. And now I can drop in the pin of choice, set up my parallel there for packing, and then I slide the workpiece down over the center pin there, and the pin is chosen to be a very close fit on the bore in the center that we're rounding over. And then I can clamp that down. The clamping bolt goes down the center, and for the smaller hole sizes where there's only a pin, then you just skip this step and use only the strap clamp on the back as shown here, because for parts that small, 1 clamp is enough. Then you just offset the X of the table to the radius that you want, accounting for the width of the cutter, of course. And if it's a tough material, you can move further out than that and do it in multiple passes, or you can do this all in one pass for something like brass. But I'll show you multiple passes here so you see what that looks like. So I moved well clear of the corner of the work, which is the first thing that will touch the cutter. And then I do a full lap on the rotary table. Then I move in on X and just continue until my X value reaches 0, where I had set the radius of the final desired cutting radius. So there's nothing magic here. This is a standard end rounding setup using a rotary table. This is normally how you would do it. It's just that the fixture that I made has just made this very, very quick and easy to set up. Hopefully so easy that I won't think twice about rounding the ends of everything, because normally setting this up is kind of a lot of work, and so you only do it when it's really critical that the part have a perfect radius on the end. So after multiple passes there is the end radius. Now you can see it's slightly asymmetrical, and that's because my hole is not perfectly in the center of the part. Now I did that intentionally to show you what happens if the hole is not centered, and definitely not because I was lazy and in a rush to get this video out. This fixture has a second variation that's common, which is dog boning a part. So this might be for like a pulley shackle or a connecting rod on an engine, something like that. You start by plunging both ends of the dog bone feature, and you plunge those first because that's a lot less chattery than trying to push the entire end mill sideways into the work, and then do your rotational pass, and then you end up in the other side that you've also already pre-plunged. And easy peasy, instant dog bone cut. Again, this is something that's quite a lot of work to set up normally, and this fixture makes setting that up take seconds instead of 20 minutes. It's a very nice looking dog bone, especially including that extremely pedagogically strategic flat spot that's there entirely for your benefit and was definitely not a stupid mistake. Quiet. Then when all is said and done, I can just tap the mandrel out of the center of the rotary table there and store it with all of the little pins. Speaking of storage, I went ahead and 3D printed a little box here to store all these bits together with my rotary table. The base has the hinge holes already printed in it, so I used that as a guide hole to drill out the lid, and that's drilled ever so slightly smaller than these little nails, which I can then just push in and form hinges. It's looking pretty snazzy there so far. And then to keep the lid closed, I 3D printed a little cavity there, slightly smaller than one of these little neodymium magnets, which I can then tap into place. And then over in the lid, I left a little pocket in the 3D print, which I can super glue in a little piece of metal there to grab that magnet. And that's a nice, easy way to do a closure in a 3D printed box like this. There's a little storage space there for all of the pins. There's some extra slots there for making more pins in the future. And then, of course, the mandrel itself. And a little miscellaneous bin there for the hardware. And there we go. That is my corner rounding / end rounding fixture. I'm going to get a lot of use out of this on upcoming projects, so stay tuned for that. You'll see it in action. Thank you very much for watching. Thanks to my patrons for making all this possible, and I'll see you next time.